Hello, thank you for taking your time to view our presentation. We are Group 3, which consists of myself, Bosco, and Jaime. We will be covering parts of Chapter 5, Systems VVT Methods Testing, in our textbook handbook, which is Verification, Validation, and Testing of Engineered Systems. The topics we will cover in this presentation all relates to black box testing. A recap of black box testing is a test involves testing a system with no prior knowledge of its internal workings. For example, a tester provides an input and then observes the output. So this is important because we can identify how a system responds. If it's expected or unexpected, we can see the response time of that system and any usability issues or reliability issues. So the three topics that we will cover in black box testing is high volume testing, special testing, and environment testing. One of the topics is high volume testing in black box testing. So high volume testing is a testing technique which allow a variety of test goals, including the discovery of hard to reproduce bugs, which can enable new levels of quality assurance when applied. So in our project, in our classroom, there's three projects. There's our project, which is the smart coffee maker. There's also another one with the parking app and a sensor for crops. So high volume testing would be very beneficial for all three of our projects because it can determine if, hey, does our system makes enough coffee in a day for the users that are wanting to drink coffee, or if there's the parking app, right? If there's so many users in the mall looking for an app, and if they're using the app all at the same time, will the app still work? Also, for the crop sensors, if you put the sensors all over in many acres of a farm field, will they all still work if there's so many units that are operating all at the same time? So under high volume testing, there's actually four subtests. One is automatic random testing. Second is performance testing. Third is recovery testing. And the last is stress testing. So these are all different types of high volume testing, and we will review them now. Automatic random testing is part of high volume testing. So in this type of test, we pretty much throw in very large quantities of random inputs into the system. So this way we can test its behavior to see how it can handle these inputs. And it's very good because usually it's automatic and it can test out the system performance and see any unexpected conditions. Usually these tests run very long, and it will pretty much cause your system to have memory leaks or any corruptions, and pretty much the system will run into failures. This is good because we can actually see when the system fails, and that can help us in the future to determine, hey, this system failed at this X amount of input, so let's have their system not run to that value. Performance testing in high volume testing is to demonstrate the system it meets the defined set of performance requirements. So, such as in our class right now, we are doing the smart coffee maker, and we set the performance to make at least more than 100 cups of coffee a day. So that can be a form of performance test that we can do to see if it can reach that amount or more. If with this test we can see that if there's any performance bottlenecks in the system. Also, we can verify that there's no fault in performing the system at full load. It can also actually establish a baseline for future tests, right? So if it can do more, then we can see, maybe we can find out that, hey, more than 100 cups of coffee a day is possible. So maybe we can raise it up to 150 or 200. So we can see if the system operates at full performance when the load is nominal intended for the environment. So a tester must verify whether each system parameter meets its requirement performance under the requirements load. Recovery testing is a form of test in high volume testing to see if a system fails in many different kind of ways, and then to see if the system can recover from that failure. Recovery testing is to inject some fault into the system, and we can see its behavior. Usually an engineer that is working on recovery tests have control over these failures and malfunctions, and have a way to log and detect why it failed, so we can prepare in the future to fix those problems if it arises. Stress testing in high volume testing, black box, is to operate the system beyond its capabilities. For example, if a system is rated to work an XX amount, we go beyond that. We stress the system as much as possible to see how it performs and its breaking points. We do it on purpose to stress test, to break the system and exposing the system to see where it went wrong, where it failed, and we can use this data and findings to determine future tests or production. If once the system is in production or being used by the users, we can determine how many people can use it, or how much the system can be under stress before reaching to a breaking point, and we can handle that and either stop the system or the product from reaching that point. And next, I'm going to hand it over to Jaime. He's going to be talking about special testing in their black box.
Okay, so section 5.5 is all about special testing. We're going to break it down and see how it interacts with the projects that are currently in the group by other teams. Usability testing. So usability testing is just random data inputs being implemented to the system to test its behavior. They typically consist of large quantities of data. So it's a bunch of, let's say, for example, fake inputs that are put into the system to see how it behaves, whether it be like if there's a power outage or if there's a issue with the hardware. Usability testing is primarily focused on testing that and see how it behaves. Usability testing tests the system versus large unexpected test scenarios. So the best way to test something is to put it outside of its comfort zone and see how it behaves when it's faced with something like that's out of the ordinary that the product or the system has never been tested for. This is, however, risky because the output that this type of testing generates isn't very I guess for lack of a better term, useful, or not useful, but like reliable. And so some of the output values generated from that type of testing can be, it's a 50-50 chance that it's going to be able to be used. During usability testing, however, some of the observables of interest are the level of the user satisfaction with the task completed. Like how happy is a user how happy is a user with the product after he or she did the task. Like for my project, for example, it's coffee maker. So throughout this presentation, I will be referring to the coffee maker. How happy is a user completing tasks with the coffee maker? That's one observable of interest that usability testing tends to focus on. The efficiency of the system performing the test, like how well is a coffee maker in making coffee, doing what it has to do. The degree of success the user will have learning the system, like how good will the user be able to learn what he or she needs to do to work with the product. And finally, the user error during the system, like how much error does a user commit, how many errors a user commits while interacting. Like those numbers, however, have to be very low. It's better for the user errors to be very low. That way it shows that the system is a bit more successful than it needs to be, and it's completing the task that it's intended to do. Usability testing reveals system defects. Defects can be good and bad. For example, defects contribute to the improvement. If there's defects in the system where it can't really understand, or say for the coffee maker, say it can't take them so much amount of coffee grounds, so that'll tell us, hey, well, we need to make the container for the coffee a bit smaller. Defects contribute also by evaluating whether the system has the functionality the user wants, evaluates how easily the user learns how to operate the system within a small amount of error. We can't take too long to learn how to use the system. And it also evaluates how well the user can remember how to use the system. A good system should be able to be mastered within the first 2 uses. After that, it should be almost muscle memory to be able to use, let's say, a coffee maker. Like you should already know how to use it. Nothing new. Every day shouldn't be a new learning lesson for the user. For measurements of usable testing are emotional response, time on task, accuracy, and recall. Emotional response is like how happy the user is. Like, hey, you know what? I'm understanding. This is good. I can work with this. Or if you're constantly like, I don't understand this. I can't fix this. I can't fix this issue. There's always something new. I don't want it anymore. That's bad for the product. Time on task. Like, if it takes you 15 minutes to set a coffee maker to make coffee, that's pretty bad. It should take minimal time, because nowadays everybody's busy and everybody wants to go about the task. Accuracy, how well you are in performing the task. You should be pretty accurate in implementing commands and saying what needs to be done and everything. Recall, how well you recall. I mean, this is basically what we just talked about, like how well the system will behave with the user. Like you should be able to recall all the tasks that were learned at the beginning. For lack of a better term, usability testing seems to be the testing method that ideally reflects what Group 3 or any project that has to deal with the interaction between the user and the actual product itself. So usability testing, I believe we see it on almost on a daily with a lot of other products. Next section is security vulnerability testing. This is more of a cyberspace type of form of testing. There are teams. There's one team that's doing an app for parking spaces, and I believe that this section right here would closely relate to them. Identify vulnerabilities in the system and computer networks. Some vulnerabilities that may appear in a network or a computer would be malware, virus, worms, Trojan horses, adware, crypto worms, sticky software, etc. All these are methods that a network is susceptible to attacks, and you can lose your, let's say, personal information. They can come in as an email saying, "Hey, you just won $1,000." This is a type of security testing that needs to be done to ensure that networks and computers don't fall victim to this. So the whole point of security vulnerability testing is to minimize access to system and computer network. It's the best way to ensure that this type of error, this type of risk is mitigated, which is minimize who has access to everything. Just trusted users, only let certain people use the computers. Physical locks and biometric sensors like passwords, or maybe even fingerprints if it gets to that point, or just a simple lock, so people can't use it. Some software mechanisms are like rules, antiviruses, and coding techniques. Like you may need to, an antivirus will completely block that firewall, etc. The sophistication of information technology is growing, so that means that risk grows even more. That means we all have to be a step ahead of the attackers to ensure that we don't fall victim to their attacks with firmware attacks, a virus, Trojan horse, etc. The number of malware attacks has spiked as a result of industrialization. The yearly vulnerability has also increased in correlation to the number of malware attacks. Number of malware attacks can have financially impacted companies, like financial liabilities, tech or business loss mitigation of breach, or increase in insurance premiums. I'm sure companies like, just for example, I'm not saying that this does happen, but like let's say Progressive gets breached constantly for someone's breaching their network, so they're losing a bunch of customer information. So little by little, they start to lose customers because it is no longer providing a safe network. So then they start to lose business, and then they become a higher liability, which means that they have to pay more in insurance. Secure vulnerability testing. Types of tests conducted are system tests, operational tests. Actual security tests conducted are vulnerability and penetration tests. These type of tests tend to see what the damage potential is, the success probability, exploitability and discoverability, and affected users. There's a table that's used at ranking security threats. This table will help determine the company doing the security testing to see how well, or what the risk factor is of each threat. Some security tests are like network scanning, vulnerability scanning, password cracking, log reviews, file integrity checkers, malware, modem dial-up, and wireless LAN, and penetration attempts. These are some tests that companies do to check to see how well their product is, like how safe it is. Reliability testing is it's another topic within section 5.5. This verify a system meets its reliability requirements. So essentially, it's in the name, making sure that the system is meeting the requirements and that it's reliable on that. This helps determine if the quality of the system is met, and it measures the quality of the system, and it checks to see if there's any potential future failure. They predict the potential future failure. Important for safety related systems, preventing systems from harming like users, bystanders, financial interests, environments. Let's take the coffee maker. We need reliability testing that would be done on the coffee makers to see how much the water container can withstand the heat. You don't want a water container that will melt after 80 degrees. Otherwise, you have water all over your system. You cause a spark in there, and you have an electric fire going on. High reliability systems are safer because they're held to a much higher standard. For example, transportation, space, and military. Of course, their systems tend to go through a more rigorous form of testing to ensure nothing bad happens when, let's say, pilots are in airplanes or up in the International Space Station, or trains, for example. We have seen where there have been derailments from issues, human errors, but not so much machine errors. Steps for reliability testing: establish an operational profile, construct test data from ops profiles, test the system, assess the reliability of the system. A lot of logarithmic and basic exponential models are used. Essentially, you're using a formula to get you your information that you need, and it helps you understand how reliable your system is. Search-based testing is, I don't believe that there's much to see here with this product. I mean, I'm sorry, with this class. A lot of there isn't a big code, or there isn't a group that has a product that's going so in depth that we need to do search-based testing. But I feel like it's something important to touch base on. Search-based testing does it generates test cases, discovers among a huge number of possible test cases. One generated is good according to the metric. So I guess it is good that it generates a test case that can be used. The formulation of testing enables automation of previous tasks, solves interactable problems, and can lead to innovative and insightful views of the system. So it makes the system a lot more clear, and it tells us how we can better it. Genetic algorithm, search procedures that benefit highly changed organisms. It's pretty much the same concept as like nature. It's implemented here, and same concept is applied in the system selection. Search-based testing can increase effectiveness and efficiency. Its generated test cases will evolve, much more improved. The test cases that are evolved are much more improved and need to be done over successive iterations. We can't have a failure going on. Evolutionary testing, search techniques for test cases generated. Essentially, it's just finding test cases that it can be used on the system and to better understand. So there's a generic algorithm lifecycle chart that I've got ahead and put it here, and it shows you how it's going to start from the basic generic algorithm lifecycle, then it goes into the testing cycle, and there's two options, either termination or initialization. Essentially, after monitor results, essentially the test results, it would go either into termination and initialization, depending on how it behaved. Mutation testing is the final section, section 5.5, subsection, I mean. This is also known as error seeding and fault seeding. This measures adequacy of test cases to estimate measures of the amount of defects left in the system. It understands the system under test. It helps us understand the system under test reliability. So defects are introduced into the system design or implementation, usually done one at a time. Temporarily modified systems are called mutants. And so there are many versions of the mutant of the system created. Each are called mutants. Mutants are expected to fail, but the real goal is to have them succeed so that it will expose weaknesses in the test case. Testing is essential in pointing out unintentional faults. Primarily, this is done in the development stage, which is essentially the best stage to do it. Initially designed systems will be faulty, but very close to the intended design. Mutants are created to make a near-perfect system correct with minor changes. So as the mutations progress, each one will be better than the last until we have a near-perfect version of the original system. These testings allows the evaluation of the test case's adequacy. Defects falls in a defective system. So if the test case is not adequate, then there's an issue there that has to be addressed. A collection of adequate test cases will distinguish between a mutant and the original system. Each mutant will generate a different output than the original. Identical results by mutant shows the test cases are inadequate. So if we keep getting the same results after mutant, after mutant, after mutant, something's wrong with the test case, rendering it inadequate. If a mutant is able to identically replicate the original system, the testing will not kill a mutant. Calculations will be needed to determine real fault presence. So it'll be so similar to the original system that the testing won't say, hey, kill this mutant. No, there's something wrong here. It will just say there's something wrong here, and it will determine, like, well, we need to do some testing to determine where the real fault is, because there has to be a fault. And before moving forward, the testers and the systems engineers need to address this so as to ensure a better product is generated. And that's pretty much it for section 5.5. So there we go.
Thanks, Jaime. The next topic we will cover is environment testing for black box. Environment testing is a test where it takes place in the surroundings or environment or area in where the system or product resides and operates. There's about 5 tests under environment tests. First is, which is environmental stress screening, ESS testing. Second is EMI, EMC testing. After that is destructive testing, reactive testing, and temporal testing. Under environment testing, we have environmental stress screening testing. So this test is during the manufacture or assembling packaging process. We can see and eliminate any defects in the system which are introduced during this time. So we can see if there are any manufacturing defects in the system, if it's caused by any electronic equipment, caused by any error defects, or any faulty parts in the equipment. We can also use this test to identify any design problems that has been brought up that are very fragile and it doesn't meet any of the qualification, and also the reliability of the growth tests were not effective. Next is EMI, EMC testing. It is a test to verify if the correct operation of the system in the electromagnetic environment where different equipment may emit or susceptible to electromagnetic interface effects. So basically in our class, we have our project, which is a coffee maker, and there's also another project of the sensors for crops. So these two hardware, the coffee maker and sensor, might be susceptible to electromagnetic environment because there's things like the motherboard or computer chips inside these two products that we have. So we must test to see if both are susceptible to this interference. If it does, it might affect performance or affect like the output of both the sensor or the coffee maker. So we have to verify it under test operates with adequate safety margins without malfunction and degrade of performance. We verify the system does not emit to the environment also, that our system does not emit electromagnetic to the users that are drinking the coffee or the crops that are growing the vegetation for the users. And then we must test that it meets appropriate standards and regulations. Destructive testing is next on the environment testing for black box. Destructive testing is pretty much destroying your system or test on purpose. But for gaining valuable information and data, this test, when destroyed, is experimental but has some numerical simulation as a backup. This is a physical test which can reveal hidden system defects that can only occur with destroying the system or product. And it is not possible to conduct these tests in early requirements. So this is pretty much in the final, near final end of the system. But these tests can be very costly and very wasteful. So if these tests are performed, it has to be very, very carefully planned ahead. React testing is the next testing under environment testing. It is a dynamic test where you test the system with an individual test to see the effects of the behavior of the system. It's usually a test where we have to see if there's a nonlinear or erratic behavior of the system, and the test covers a large number of input data. So with this test, usually done in a test facility, it acts as the real environment of the system that is under test. So again, this system test is tested to see the effects of the behavior of the system under the test. Temporal testing is the last of the environmental testing. It is to verify the timing of the system, pretty much in the range of the best case execution time and the worst case execution time. This test is to see any timing issues in the system, and it is very complex because it has to have requirements such as timeliness, simultaneously, and predictability. So when test engineers test on here, they have to generate a set of test cases that sees the system behaviors that are likely to reveal temporal defects. And this is the end of our presentation. Thank you very much, and we hope you enjoyed our presentation on Chapter 5 relating to black box testing. Thank you very much, and have a good day.